Welcome back to the next lecture, which is about dimensional analysis. Another methodology to scale up and scale down biophysical chemical systems is to carry out a so-called dimensional analysis. Before we start, dimensional analysis is at first skill relatively straightforward, so it is a very practical approach to analyze complex situations. However, the methodology requires insight and experience. It always gives an answer, but wrong choices result in misleading answers. Therefore, it can be dangerous methodology, a tool to be applied with care. In this lecture, the methodology will be explained using a stirred tank as a case. We will answer the following question while scaling up a stirred tank reactor. How can we keep the volumetric power input the same? Dimensional analysis follows a four-step approach. Step 1 is to choose one physical or chemical quantity that is to be analyzed, and n-1 quantities that explain it, according to your insight, knowledge and/or experience. Note that in some cases this leads to very detailed choices. For example, consider pulling a body through a viscous medium. One wants to analyze the power needed to do so. Insight will tell you that the dimension of the body will play a role, but which dimension? Is it its length, its diameter, or both? And how to describe its exact shape? Remember my earlier warning on the use of the methodology. A wrong choice of quantities can lead to a wrong answer. But let that not stop you from trying. In step 2, we write the relation between the investigated and the explaining quantities in a generalized format. A dimensionless constant multiplied with the product of the explaining quantities, each with an unknown power coefficient. This means that we have n-1 power coefficients. Here's the example for dragging a body through viscous medium. We are already at step 3. We now write down the units of all the quantities, each uniquely expressed in the basic units of length in meter, mass in kilogram, time in seconds, and temperature in Kelvin. The expression that was set up in step 2 now leads to a set of linear relations between the power coefficients to ensure that the expression is dimensionally correct. The number of linear relations equals the number of basic units, which we define as m. In case the number of linear equations matches the number of explaining quantities, we can calculate all coefficients and we end up with a single dimensionless group. In case there are more explaining quantities than basic units, there's more than one dimensionless group, and the number of dimensionless groups equals 1 minus n-1 minus m, which equals n minus m. This derivation of the number of dimensionless groups is the so-called Buckingham pi theorem. Finally, step 4 is to find the dimensional group. This again requires choices to be made based on insight or experience. One chooses m power coefficients that are expressed as linear relations of the remaining n minus m minus 1 power coefficients. And these linear relations can be solved. When substituting the solutions for the powers in the original expression of step 2, and then rearranging the terms until we obtain only groups with a common power coefficient, we will see that the original expression has been transformed into an expression of n minus m groups in accordance with the Buckingham pi theorem. Moreover, we can check that each of these groups is indeed dimensionless. At this point, the dimensional analysis has delivered the expression that describes the system in dimensionless terms. We still have one constant and some unknown power coefficients, and those need to be determined from experimental data. Note that we have assumed that the system can be described by a power function, but this was not based on first principles. Therefore, the power function must be considered as an approximative description that will only hold for a limited window of operation. I started this lecture by stating that this is a methodology that supports scaling up or down. So, how do we apply the obtained expression? If we scale up or down while keeping the value of each of the dimensional groups unchanged, we can expect that the systems will perform identically on both scales. Note that it doesn't mean that each of the quantities in the dimensionless groups will remain equal. For example, groups that contain a dimension of the system will by definition change upon scaling up or down. If these change, it means that some other quantity needs to change as well to keep the dimensionless group constant. Or alternatively, entire dimensionless groups may even change upon scaling up and down. But in that case, other dimensionless groups can be changed such that their product remains unchanged. It is time to illustrate all this theory with the example of the stirred tank. In step 1, we consider the system and we come up with 9 dimensions and physical quantities, all expressed in their basic units. Our insight can help us realize that if we keep the scaled system geometrically similar, that is, all dimensions are scaled proportionally, we need in fact only one dimension to describe the system. And we have 6 relevant dimensions and physical quantities left. Step 2 now yields an expression of the power input as a power function of the other 5 quantities, with 5 power coefficients. Then step 3 follows, in which we find that the 6 quantities have units that form combinations of the 3 basic units of length, mass and time. At this point, let's make a small sidestep to the Buckingham Pi theorem that tells us that there then must be 6 minus 3, so 3 dimensionless groups. We write down the 3 linear equations that keep the overall expression dimensionally consistent in terms of the basic units, m, kilogram and second. Now we have to choose 3 dependent power coefficients that are expressed by the remaining independent 2. Note that the dependent power coefficients will appear in multiple dimensionless groups and the independent ones will appear in only one. In this case, we choose viscosity and gravity as the independent ones. This results in the following 3 linear relations which can be solved for the 3 dependent coefficients. Finally, we substitute the obtained relations for the independent coefficients in the overall relation and obtain a new overall relation consisting of 3 dimensionless groups. Experience tells us that the 3 dimensionless groups that we have thus obtained are in fact well-known dimensionless numbers that are called the power number, the Reynolds number and the Froude number. Our original question was, how do we keep the volumetric power input the same while scaling up the stirred tank reactor? Well, we can write our overall expression for the power as obtained from dimensional analysis for the 2 scales and divide by the respective volumes. The 2 scales must be equal. In case we use the same fluid in both systems and suppose we stay on planet Earth, we can eliminate the quantities of viscosity, density and gravity from this equation. And now we obtain an equation containing as only quantities d, which is the length scale, and n, which is the stirrer speed on both scales. In the final step, we fill in the scaling ratio d2 over d1. And we can now calculate the ratio of impeller speed, so n1 over n2, for which the power input per volume remains the same at both scales. So hereby I conclude the dimensional analysis, and I hope to see you back in the next lecture.